We go back to the video. Uh, hold on. Order, second order. Every degree of freedom gives you one equation. We have our free body diagram. Weight and normal force don't need to be included because they're equal to each other. Inputs, outputs, helpful for our final equation. FEM causes a change in the system. And then X should be our output. Displacement should be our output for mechanical system, but it also includes the velocity and acceleration, all the different derivatives. Now we get to our definitions. So the equation sheet is where we're going to pull from this. Again, I want to write this out. I want to just get it all down on paper, and then I'll put it together. I'm not going to try to skip any steps because that's where problems can occur. So we have sum of forces equals mx double dot. That's my starting point for a translational system. We have FEM, our electromagnetic force, but that's just an input. I don't need to define it. I don't have anything else to go with it. Now we get to our other forces on the free body diagram. So we have a spring force and we have a damper force. We talked about this last week. On the equation sheet, the definition of a spring force is K delta X. The definition of a damper is B delta X dot. So let's revise these definitions because they're not quite done. I don't want to have any deltas in my final equation. I've seen that before. I want to expand this out, get rid of stuff, just make sure all the definitions have variables that are within the free body diagram. So what should we change K delta X to? Just KX. Yeah, you're right. Why is that? Well, again, both of these are tied to a wall. So I could think of it as, well, I know it's in compression, so I've got my delta X would be X minus 0 because that side is not moving, so therefore our spring force is just KX. For my damper, we've got B delta X. This is also just like it, X dot minus 0. The other side doesn't move, therefore we have BX dot. So I've got my two definitions for my other two forces. My free body diagram has 3 total forces on it. One of them is the input. And so now we are going to put it together and solve and create the transfer function. Put it together? All right, let's do it. So we're going to start with the equation like that. We're going to then look at the free body diagram to figure out what are the sum of forces. So let's go back to that diagram. Which forces are positive? Electromagnetic force is positive, right? Because we're following X. So FEM is positive, the other two are negative. So this is equal to FEM minus spring force minus damper force. Sum of forces equals mx double dot. Free body diagram, I have my sum of forces. Now we can use the definitions that we put down. So I'm going to replace spring force and damper force with their definitions. And lastly, all of the x's are related to each other. I want to get them all to the same side. So that means I'm going to add them to the left-hand side. I like to start with the highest order derivative first. So we start with mx double dot. Then we add bx dot. So that takes it away from the right-hand side. And then we have kx equals FEM. That is our one equation for this problem. couple things that we want to check. This is the output side. Is it all positive? It's all positive. Check. That means it's stable. And that's what all of our problems should be. So if you got on the homework, if you've got some negatives on this side, now negatives don't matter on the input side. They do matter on the output side. If I have a negative, I probably defined something wrong. Maybe my free body diagram didn't match up with my definition, something like that. The other thing that we want to check is we said it was second order. It is second order because I do have that x double dot. So I've got one equation, second order. So all that prep is just kind of figure out. The other thing was our inputs, outputs. This is my input, these are my outputs. So those are just kind of the steps of Bobati to make sure we're kind of on the right track to get to that final answer. Questions? How much? Okay, last step. This is only if I have a single input, single output. If I don't, I can just leave it like this. Sometimes we can combine things if it's a higher order system, but the last step is the transfer function. You don't have to write this down at the bottom, don't worry. But transfer functions, did you use them in circuits at all? Are you familiar with the term? Transfer functions are a convenient way to represent an input-output relationship if it is single input, single output, CISO. If it is CISO, we can create a transfer function. If not, I'm not going to do the final step. These are based on Laplace transforms. These can be helpful to solve our differential equations. These convert linear differential equations into algebraic equations in terms of the variable s. Now, this is the official Laplace transform. You are not doing official Laplace transform in this class, really. We've got tables and stuff, but what we're trying to do is take that equation and change it into the S domain, which makes everything algebraic. It makes it a little bit nice and easy to use. And MATLAB understands transfer functions. And so we can basically set up block diagrams and everything to connect different systems. So how, you know what, that's on the next slide. Again, we're going to the S domain. Chapter 8 kind of goes through this a little bit more, but why are they useful? They're used in a lot of block diagrams, MATLAB, Simulink, so we'll use it quite a bit. But we can do this without the formal Laplace transform. I don't have to take an integral and all that stuff. It's really easy. Let me show you. Let's say I've got you don't necessarily have to write this down because we'll do it with our equation. But if I have a third order equation right here, so I've got a triple dot, y triple dot. What we're going to do is we're going to replace all of the dots with s's. Dots become s's to create a transfer function. Now, if you remember back to some of your differential equations, what this means is that we're not dealing with any initial conditions. So we're saying that, there's no initial conditions, there's no stored energy. The dots become s's. If I don't have a dot, that just stays as is. So like this just stays like that. This just stays like that, but any dot becomes an s. And what that allows us to do then is to combine all of those terms together, because now they're all multiplied by the same output, y. We have our input, so we can also combine those. Our transfer function is always output over input. So that would mean y over u. So I can divide the u, put it down here. Then I can take all of this and put it under here. That creates our transfer function. Y over u equals, this is my numerator, this is my denominator, it's got s. Why is this helpful? Down the road, we're going to deal a lot with transfer functions. So by putting it in this form, I have my input coming in. I have my transfer function like this. So if it feeds in the input to this transfer function, it's going to spit out the output. So I can put a force in here. It's going to spit out displacement, acceleration, velocity, all out of that transfer function. So the main thing I want you to know, because we're not really going to get to analyzing these in a while, but dots become S's, combine all the terms, then we want output over input equals something with S's. Shall we do the problem we were just working on? Okay, it's pretty easy. We have mx double dot plus bx dot plus kx equals our force. So dots become S's. Because this is CISO, single input, single output, this becomes ms squared times x plus bs times x plus k times x. Notice that I capitalized them. That's just to show I'm not really in the time domain anymore. I'm in the S domain. So I'm just showing it's a little bit different. And then we have our force over here. I can say this is my force in the S domain. It's a function of S, no longer a function of time. So now we want to get all these combined. So we have ms squared plus bs plus k multiplied by my output x equals FEM. And to get our transfer function, we want output over input. So I know that the x is my output side, FEM is my input side. So I want to get x over FEM. We're going to get a transfer function that involves s's. What is my numerator? 1. So if I divide both sides by FEM, I'm left with a 1 on the right-hand side, and then I'm going to divide both sides by that polynomial. We get 1 over ms squared plus bs plus k. Good? All right, cool. So what I'm going to do, I'm going to let you try one yourself, and then we will take a break. So you'll probably just need 15, maybe 20. You're just going to use full body. You can always ask for help if you feel stuck, and then you can check your final answer with me. Once you complete it, you can obviously help others, but you can work with the people that are around you. I'm just going to give you this problem, which also comes from the textbook. So use full body. Use it on all the homework. Use it on the test. Follow the same process. Don't try to skip ahead to the final. That's where mistakes can happen. So take some time and work on this, and I can help you as you go. Yeah. We should have. Then it comes down to direction. But once we have that, how the part builds. Yeah, that's me. Is that the weight? What is the definition of weight? Just mass times gravity. That's it. The weight is just mass times gravity. Now, gravity is not the same as the acceleration, but it is a acceleration acting on the body. Oh, yeah. That's good. Good check. Okay, this is my free body diagram. We need to find the full notes that the spring is the big part of it. So the spring starts at an unaffected. No. My wife went over the Nile. This bungee jumping. It was extremely scary, right? But she survived. But the bungee jumping, right? You start undeflected, and then gravity lets it. But ultimately, you're not going to hopefully hit the ground. It's going to oscillate a little bit. Got stiffness in the. So why are these arrows put it up? Technically, here's what I want you to now let's not look at other forces. Look at okay. Look at the positive displacement. So yes, it is in this case reactive weight. So it's going to try to pull back hard. However, forces can sometimes like not so much based on forces. Make sure you're looking at positive displacement. If this is moving positively, the spring is going to be in tension. It's going to try to pull back. If it's moving positive friction, it's going to try to pull back. So I would always look at this for our direction of forces. Probably should have been wearing that. Keep working on it. I want you to solve it. Try to get that. Well, I fill in the video. So the reason why FK and FP, both those forces, we are not looking at the weight. We are looking at positive. Instead of positive on the ground. As the mass moves down, bringing the tension of the back on also. So only look at the axes, force directions for components that are at least tied to a wall. Yeah. But it's a little different input. So inputs and outputs. You could say the weight is the input, or gravity. Gravity is really the one that's driving this. Um, obviously, our output is going to be x. And then we have our definitions. These are very similar to the one that we did. Obviously, we have weight, but everything else is the same. So for the second D, body, we are going to take that first equation, Newton's second law, and we're going to plug in using the free body diagram. Now, just be careful what is positive and what is negative. We just want to be consistent, right? So let's, oh, you know what? I have it. So weight, because x is positive going down, we have W, weight, minus the other two. So we can put our definitions in. And we're almost to the transfer function. This is going to be a transfer function because it's got single input, single output. Are there any questions, anything not lining up with what you got that you're not quite sure about? Okay. So I'm going to do the same thing. We want to get all the x's together on the same side. So we're going to add them to both sides. So we want to go from highest order to lowest order. So that gives us this, and it looks very similar to what we had before. It's just our input force. What's driving the change is going to be a little bit different. So, questions? Good. Keep moving. You know what? Let me just box this too. We're gonna create the so we're taking it from the time domain to the S domain. That means we can group all of these together. Now you can think about the weight as the input. However, like if I want a nice model for what happens if the weight, so for the bungee jumper example, right? If I have a bungee jumper, does their weight change maybe person to person? Possibly. Might that affect the amount of rope, the length that I give them on the rope? Well, maybe, right? So if I wanted a model for that, look, I know the stiffness, I know the damping, but like what kind of length should we have? Because the heavier object is going to have, it's going to go farther, right? So we don't want them to hit the river or anything like that. So I would actually say, instead of just total weight being the input, it really is just gravity. Gravity is what's driving this. Gravity is my input. And so in that case, my transfer function would be x output over g gravity. That way the m, the mass, is in my transfer function. So if I've got from jumper to jumper, I've got different masses, that goes into my transfer function. We can actually see over time, like what is going to be the lowest depth that they're going to go to. If we're going from a 100-pound person to a 200-pound person, that's going to change that lowest depth. It's going to change where they end up at, their final static point. Does that make sense? Yes. Why G is in the bottom? Yeah, so I could put, this is my weight, right? Mass times gravity. That could be my input, but because it has mass, it's really tied to the mass spring damper. So I want that mass to be within my transfer function because it does make a difference. It can change if I change the mass. And so instead of having a constant weight, what we have is a constant gravity. So at least my gravity is constant, and then my mass is now in my transfer function. So it's really output displacement, input gravity. Other questions? So force doesn't have to, the input doesn't have to be a force. In this case, it's an acceleration. Okay. Real quick, before we do another quick section, or take a break, actually, can we recreate the model to account for static deflection? What's going to happen with this, like with the bungee jumper, they're going to jump, and so they kind of oscillate a little bit, oscillate, and then they reach some kind of steady state position. So what would happen is that, this would turn into, maybe we've got our mass way down here, and the spring is now deflected, and we've got our damper looking like this. So we started with an undeflected spring. It goes, they oscillate a little bit, and then they hit some kind of steady point. We could call that something different, like Z. Now, the book goes into this quite a bit more, but what happens now at this point right here, this is where Kx is equal to mg at this point. Does that make sense? So now the spring is deflected enough where, based on that spring constant, those two forces cancel out. So statically, this is my just Kx. This is my weight, mg. And they cancel out. So now it's no longer moving. We can create a new equation for this using z, where z is basically x minus whatever this distance is. In this case, we could create a new equation. It still has the spring and the damper, but mass, the weight, is no longer a part of it. So my equation could just become, we do sum of forces equals mz double dot. This is equal to, we have a negative spring force, we have a negative damper force. So we have mz double dot is equal to negative kz minus bz dot, and we get to our final equation that looks like this. Really two different models for the same thing. This is where the spring is undeflected. This model is for when the spring is deflected. So we already have the weight is canceled out by that kx. We have our new starting position. So we've got a new start position where the mass is canceled out. So our free body diagram only looks like this. Now, how is this useful? Like, what happens if I don't have any input force? What's going on here? Well, we can actually, if I, let's say, move this, so I have a starting z that's different. We can move it all the way back to that starting x position and let it go. It's going to move the same way that this one did. And so the model still kind of holds up. It's just in this case, I don't have a starting force, whereas this one had that starting weight. So it is possible, I just want to show you, to make different models for the same system. It just kind of depends on where your starting point is. But we don't deal a whole lot with this. It's just another way to look at it. I'm going to leave this up here. Any questions? All right. If you got questions, we'll take a 5-minute break, and then we're going to look at rotational systems. So let's come back at 8:18, and then we'll do a few more examples. It's the real scramble. I'm surprised they can make us meet the first week because it's like don't really check anything until like Monday, and it's like, well, big scramble. Yeah. Say it again? Oh, less by far. I'll take any class 10 or less. That's great. That means everyone can get a lot more individual help, and uh, I think I have it open after test one. You can't submit it if it's not open. Gotcha. Okay. We're going to transition to rotational problems, but before we do that, there's two major mechanical transformers that we want to look at. Optimus Prime and who's the other? Bumblebee. We've got two major ones. The first one we're going to look at is a lever. In some of your homework problems, you may have some kind of bar that connects two translational elements or two translational parts. And so this is really about translation to rotation. What we're going to use in this class is called the small angle approximation. Small angle approximation allows us to linearize the system. Now, in some cases, I won't be able to linearize it. Sometimes I have a full 360 degrees rotation. But if we have applications where there's only small movements, such as maybe less than 10 degrees, that's where we can use the small angle approximation. And the small angle approximation goes like this. Here is a right triangle. Here's my angle right here. What would this top side be? If I have got my right triangle, I've got my angle. What is the length of this line? If L1 is the hypotenuse. What? Not quite sine. Not L1. So it's not sine and it's not just L1. It's okay. Yeah, thank you. L1 cosine. Wait, not con. Cosine theta. What does that make the other side? This one is L1 sine theta. Now, sine and cosine are nonlinear. So if I put that into my equation, I can't create a transfer function. I have little analysis tools. But if we can approximate only small movements, these change. So I'll tell you what these change to. Cosine theta, because it's such a small angle, we can just turn this into a 1. Cosine theta just becomes 1. So this all just becomes 1. Therefore, for small angles, we can approximate that this side is basically the same length as the hypotenuse. Does that make sense? Yeah, it's pretty close at a small angle. So this side we just say is L1. For this side, though, what do you think sine theta should become? If it's really small. 0. That's the obvious choice. Sine theta becomes 0. I have 0, but that's not quite right. So, did you write it down? Okay, you're still waiting. The obvious choice is, yeah, let's just make it 0. But because theta is small, we don't want it to be 0 because that's going to ruin some things. Is we can approximate sine theta just to become theta, and this is in radians. So I forget exactly what 10 degrees is. Maybe it's like 0.05 or something like that radians. So therefore, this, the sign goes away. That's nonlinear. And we're left with L1 theta. Okay. So we're going to use this on the next slide because it's going to be really important for us to, as we go through problems, I always am going to use small angle approximation in this class for creating some of these relationships. So let's do an example. Are you done writing? You got it? Okay. Let's just say I've got a force on this side and I have a spring connected here. This problem is going to be a sum of torques problem, where we have sum of torques equals J theta double dot. Now, we're not going to do the whole thing. This is just an example. But if this is rotating, and theta is a giveaway. If I have a theta, that's going to be a rotational problem. That's a sum of torques. It's not a translational problem. So I have sum of torques. What would the torques be? So I can draw like this circle here. This is J. This can represent my bar. I'm going to have a torque from that force going this way. The torque of force 1 is going to create a counterclockwise motion, or a torque at least, for this bar. What would the kind of torque? This is going to give us a torque as well. Which direction would that go? So if this is pushing it, it's going to compress the spring. So for a positive angle here, it's going to compress. Therefore, it's going to push down. And it's going to give us a torque like that. Thing is, these are translational elements. The force is translational. It's linear. It's not actually a torque, but it can create a torque. The spring is also translational. So we're going to have to define some of these things. What is this torque equal to? This is the easier one. Think about dynamics or statics. What is, maybe you think of it as moments. Okay, torque is the same as moment. What is the torque about this point using the force? F1 times L1. Now I would say technically it's F1 times L1 cosine theta, but you beat me to it. You're already thinking small angle approximation, right? Maybe? Yeah, of course. Because this force is just moving down. So, as this moves, it's not necessarily at a right angle. And so this torque would be force times L1 cosine theta, but for small angles, this becomes F1 times L1. That's my torque there. For the spring, TK, it's also similar. It's going to have a spring force times, in this case, it would be L2 cosine theta. But small angle approximation, that would be FK times L2. Because again, small angles, we can basically say that length is not going to change. But what is F sub K? What is that spring force? This is where it gets pretty tricky. So for that spring force, if I zoom in a little bit, so this is my theta. What we really want to know for the spring, because it's a translational spring, is we want to know what this delta x is for the spring. That's how much it's going to change. This is L2. So what would you say this delta x is? Because we know that the spring force F sub k is equal to k delta x. Now it's fixed up at the top, so the only delta x it's going to see is right here. What is delta x? You can look at it as a triangle, right triangle. It is. So this would be k delta x is the same as, because this is a right triangle right here. Delta x is the same as L2 sine theta, which for small angle approximations just becomes L2 theta. This is kind of hard stuff. That's why we're going through it. But this is how the spring is related to theta, because it has to be related to theta. Everything is related to theta. So as theta increases, that spring compresses more. Therefore, I have more force. Theta increases, force increases. Therefore, I'm also increasing the torque. So that means that Tk, my spring torque, if it's this times that, is equal to K L2 squared theta. And the units of this are going to be Newton meter. So this is newtons per meter. We have meters squared, so that gives us Newton meters. The radians go away. Questions? Okay. All right. You'll have some questions. There's stuff like this on the homework. There's stuff like this on some of the participation problems that we'll get to. But that's one of the most important topics to learn for this. No questions? Mm-hmm. All right. The last transformer that we'll see it next class, so I won't go into it too much right now, but gears. Now gears, they have lots of problems. I mean, I don't know if you took mechanical design 1, sometimes you got gear problems, non-linearities, all that. So we're just dealing with ideal gears. The gear ratio is shown by capital N. That you can either count the teeth, so the ratio of the second one with respect to the first one, or the ratio of the radius, diameter, all of those kind of things work. But for the gear ratio, it's always driven over driver. So R2 over R1, or the number of teeth, N2 over N1. How these interact, we can look at the mesh. What do I have here? The speed between the two, so I can look at it like this. If I've got my driver gear here, it's got smaller. This is my larger gear. So this is R1, this is R2, but the speed between them is going to be the same. So the speed at this point, the V of the mesh at that point where the teeth interact, that velocity is going to be the same. And the velocity is equal to R omega. So in this case, because I know the radius difference, we can also say that the speeds are related through the gear ratio. And they're opposite. So the more teeth I have, or the larger the radius, I'm not going to spin as fast. So for example, with this one, if this is my driver and this is spinning, and it's turning this one. Which one is moving faster? Which one is rotating faster? Which one has a higher omega? Smaller one. This one has a higher omega. Omega 1 is greater than omega 2. Why is that? Well, because R2 is greater than R1. So if this is greater than 1, this is greater than 1. Omega 1 is faster. Torque is opposite. So torque is actually related to, it is inversely related to the speed. I can also write torque like this, T2 over T1. The larger the radius you have, the more torque you have. So in this case, I'm reducing the speed, but I'm increasing the torque. That's what's going on. So this is called a speed reducer. It has a larger torque output. So for your car, you got different gears, right? So you put it in low. What you're doing is you're putting it to a large gear like this, where I don't have very high speed, but I've got good torque. And then as you go on the highway and it changes gears for you, it's automatic, right? You're changing your gear ratio to have higher speed, less torque. Now, we can look at the torques. We can look at the velocities. There's also a common force in between here. So this, if this is turning like this, it's going to push on this gear. So there's a contact force. Maybe I'll call it the mesh force. That's equal and opposite on those gears. So as this gear is turning, there's going to be some opposition. So there's a contact force in between that's equal and opposite. That's another way that we can kind of look at the torque here. So torque would equal that mesh force times the radius. So we can either use stuff like this. We can look at one body and go, hey, I know that there's going to be some opposition. So this is one of there's a mesh torque going on here. There's a mesh torque going on here. And that's kind of how T1 is related to T2. It's all just based on the radii. The higher the radius, the more torque you're going to have. And so we're going to treat them as ideal. Nothing is lost, no energy lost, anything like that. So we'll do a problem with this next class. You feel okay as an introduction? Okay, we'll get some more practice. The last thing we'll cover today is rotational mechanical systems, which have a lot of similarities to translation. I'm going to show you this as we keep looking at different kinds of systems, but we usually have some kind of input. Force. In this case, torque. What is it doing? It's changing my position, my velocity, my acceleration. So these are kind of our outputs, inputs, outputs typically. We have our three main elements. In this case, now I'm looking at moment of inertia. What's the moment of inertia of that object? We're going to have springs, stiffness. We're going to have energy loss, dissipation. That would be our damping. So we've got similar elements. It's just going to use this. When it comes to modeling, there's no difference. We're going to treat it all the same way. We're going to do the same process. It's all similar. All that really changes is the letters. But in terms of modeling, it's no difference. Rotational system. We're going to do a lot with electromechanical like motors, right? So that's a rotational system. Anything with gears, any of that is mostly rotational. We're going to still use full body. For the order of the system, again, it's number of degrees of freedom. How many different ways can this system rotate? If you have 1 degree of freedom, that's still going to be an acceleration. That's going to be 1 second order equation. So that's what we're going for. And I think next we're just going to try a problem. If you're okay with that. And again, I will post these slides right after class. But a lot of similarities. Okay, so the problem is from the textbook. example 2.9. Now the textbook doesn't do bow body. I'm going to let you know that. I don't know why, tried and true, but this is our example. This represents from an internal combustion engine, a toroidal segment piston matched with the cylinder. They both rotate on a common axis. They tell us what positive displacement is. So if we're looking from that direction, it would be clockwise. And what's happening is that a diesel engine provides external torques, E in, that appear as equal and opposite on both the piston and the cylinder. And there is a spring in between the two. Notice there's also friction. So these are in some kind of housing. There's going to be some friction. And usually there's maybe some oil there to reduce some of that friction, but ultimately there is some kind of B value that we have to take into consideration. Okay, what's our method? Full body. This looks harder than the last one, doesn't it? Like a little bit more. No, you're not afraid. You're ready? Okay. We don't need to breathe. What would you say the order of the system is? Second order? Second order? What? Second order? Second order. Huh? Let's see. We do have one common axis. That's nice, right? So I've got my axis here. So it is all over one axis. However, do they all move? Does it all move together? Or is there a little bit of difference between those two? So what I see is that even though we do have a common axis, they move independent, somewhat independently from each other. So theta 1 does not always equal theta 2. Therefore, for J1, we're going to treat them as two separate bodies. We're going to have J1 and J2. So J1 does have 1 degree of freedom. It's going to have its own acceleration. And so therefore, that's going to be 1 second order equation. Same thing for J2. It's just it will have its own acceleration. So we have 1 second order equation for J1. We have 1 second order equation for J2. We add those two together. In total, it is 4th order. Okay. Again, you don't have to understand this perfectly. It's just, for me, I'm just trying to figure out how many equations I should have. So I'm not going to stop at one equation. I got to do an equation for each body. Each body has an equation. Each body has a degree of freedom. And so each one is going to have a second order equation. Okay, next up, we have the body diagrams. And this is where it can get a little tricky. So for my body diagrams, for a three-dimensional body, I usually put an eyeball just to represent which way I'm looking from, because I can either look from this side or the other side. It's going to change things. So I'm going to look from this side, and I've got J1 here, and I've got J2 here. And because I'm looking from this direction, these are my directions of the positive displacements. And now we fill in the forces. Now, if you have a purely rotational system, you're like, man, I really like the translational systems. There's another way that you can draw it. So I'm going to give you a second option. You can draw it like this. J1, J2, theta 2, theta 1. What I would like you to do is fill these in. So I'm going to fill both of these in eventually, but if there's one of these methods you really like a little bit more, that's fine. I'm going to stick mostly to this going forward, but this is an option. I want you to fill in the torques. There's a few torques on each of these. Some of them interact with each other. I want you to fill those in as best as you can. Maybe talk with the person next to you. Try to be on the same page. Like, hey, have we got everything? The first two are pretty easy because they're on the diagram. The other ones, you need to kind of think about. Maybe you need to use some pencil props. I got my erasers up here to try to visualize maybe what's going on. If you got any questions, let me know. Yeah, that's fine. We really close, incredibly close. You're right on the number of arrows. I just have, huh? Direction. One of the directions. Just one though. You already know which one it is? Because you were looking at the torque, you weren't looking at the positive displacement. Is that what it was? No, maybe? Oh. Uh-oh. Figure it out. So let me put the T-ins in here. T-in. T-in. If you're doing boxes, this would be T-in because it goes against the positive direction. This one is positive for J2. How many torques do you have on each body? Should be the same number for each. 2 torques on each body, 3 torques on each body. 3. It should be 3 for each. Do you remember friction? Ah, there it is. Let's talk about friction. Which way should the friction act on J2? Let's look at J2. Which way would you say the friction should be acting J2? Opposite of T-in. So this would be TB, I'll call it TB2. It is the same friction coefficient, but that torque will change depending on, because the angles won't always be the same. So in the same vein, which way should the friction point on J1? Opposite of the torque. But that would be incorrect. This was the one. You fixed it? Oh, you fixed another one. Okay. Back to bungee jumping. It wasn't about the weight. It was about the positive direction. So this friction is not pointed this way because it's fighting the torque. This friction is pointed this way because it goes against the positive motion. If positive is clockwise, friction is going to be counterclockwise. not about forces, it's not about the torque. So which way should the friction act on J1? He was indicating counterclockwise. Seems a little counterintuitive. It's going to save you a lot of headaches down the road if we forget about all the torques going on and just look at this. This friction is between the object and a wall. So the other side is fixed, right? It is purely based on what the type of rotation is. If it's positive theta, that means friction is going to oppose that. If this ever flips to negative, that's going to flip the sign of this one. It's also going to oppose it. So it's always, huh? Well, I don't know. But what I do know is that positive direction is both clockwise. What are they actually doing at any point in time? One of them could be positive, one could be negative. And then 5 seconds later, they could be flip-flopped. I don't actually know, but I know which way I'm saying is positive. So this could be quite possibly, because of the input torque, be moving negative. But that means that's going to, because this is tied to theta, it's going to also be negative. So it's going to oppose it. So that's what you got to watch out for. Last thing is there's a spring between the two. Which one is greater, theta 1 or theta 2? Because we have two ends that can move. Doesn't matter. So which one did you pick? You know what, let me just put these down here. Which one did you pick? I don't care. Okay, I'm just going to say theta 1 is greater than... Oh, you know what? No. Let me look at the torques, just for the fun of it. If this is moving this way and the torque is moving that way, maybe we can say theta 2 is greater than theta 1. Doesn't matter which way you choose it. It just depends. Like, we're just going to stick to that. So if I'm saying theta 2 is greater than theta 1, the spring is essentially like in tension. There's going to be an equal and opposite torque pulling back on theta 2 and then pulling on theta 1. Again, I like to use pencils or erasers or whatever, but I'm saying that based on the torques, this one, theta 2 is greater than theta 1, so the spring is going to try to pull this one back, and it's also going to pull this one clockwise. So okay to take your time on it just to make sure. But they should always be equal and opposite. And another way I can check myself is at the end of this. If I have any negatives in my final equation, I probably messed this up combined with my definition. Something's wrong in there. Good? Now, you could have had the other way. That's totally fine. In this case, it would look like this if I was drawing a linear diagram. These can work, I think, especially for purely rotational systems, if it's something you like a little bit better, where all of them are still negative, positive the same way. Good, move on. Okay, next one is inputs, outputs. I like to do it for every single body. So I'm going to make tic-tac-toe. We're going to do input and output for J1 and J2. J1, well, for both of these, they have a Tn. What is the output of J1? Theta 1. The output of J2 is theta 2 and all its derivatives. You don't have to write those down. So these are our outputs. Do we have any other inputs to the J's besides the torque? Anything you can think of? Okay, if you don't. If you stop here, that's totally fine. But I know that they are tied through the spring. So if theta 2 moves, that is going to affect theta 1. So we could say that theta 2 is an input to theta 1 and vice versa, because they do affect each other. All right, now we're almost to the end. So in my final equations, I'm going to have one that looks like this. I'm going to have one with these on one side, these on the other, and all its derivatives. That makes sense. And so now we get to definitions. So we're going to start with, for a rotational, sum of torques or sum of moments equals J theta double dot. TK for a rotational, and this is on the equation sheet, this is equal to K delta theta, where theta is in radians. Now, this is where I need to match my free body diagram. I said that theta 2 is greater than theta 1. So in my definition, I want this to be positive. We're going to have theta 2 minus theta 1. So that gives me a positive definition. It matches my free body diagram. When I get to the end, I should have all positive values. We have TB1, TB2. They have the same coefficient. And this is the definition for rotational damper. Again, this could represent a fluid in the housing, some kind of friction. What would our delta be? Theta 2 minus theta 1? Or theta 2 dot minus theta 1 dot? Thank you. So the friction is not seeing the total, all of the thetas. All it's seeing for TB1 is just seeing this rotation with respect to a wall. And so there's actually no delta. This would just be, if I could say it's theta 1 dot minus 0. So that's B theta 1 dot. And likewise, TB2 is going to be B theta 2 dot. So it is just seeing the velocity of that object. The only thing that is tied between the two is the spring. Now, if I had a damper in between the two, that's where we would use the delta theta. Okay, we're almost there. Now let's diminish it. So I'm going to take all that information that I have. I think I got everything. And we're going to create two equations. So let's start with J1. We're going to do sum of torques equals J1 theta 1 double dot. Do not forget when I'm doing this, especially because now I've got two thetas. When I'm solving this, this is for J1 and this is for theta 1 double dot. So that means I'm going back to my free body diagram and I'm looking at all the torques. What are the positive torques for J1? What? TK. TK is positive. The other two are negative. So we have TK minus TB1 minus TN. So now we put those definitions in. We have K times theta 2 minus theta 1. We have B times theta 1 dot, and we have a negative Tn. What's my next step? Oh, we were going to get out early. No. S is not quite. Not quite. Not quite. Yes, outputs on one side. What is the output for this, for J1? We put it in our little table. Theta 1. Theta 1. I want to get all my theta 1s together. See, I got theta 1 on the left-hand side. I've got theta 1 here, theta 1 here. Those are negatives. That's good for me because I'm going to add them to the other side. So we get J1 theta 1 double dot plus, I'm going to go with the next highest derivative, B theta 1 dot plus K theta 1 is equal to K theta 2 minus Tn. This is our first equation. These are all theta 1s on the left-hand side. This is my output side. Is this good? Is it done? Well, it is one second-order equation. I did identify that theta 2 and Tn were inputs, but is it stable? Did I do things correctly? So the output side is all positive. Positive, therefore it checks out. If I had a negative theta 1 anywhere over here, which could happen based on my definitions, or maybe I did my algebra wrong, just moving them over here, then I would be like, oh, I did something wrong. But all of the theta 1 side is positive. So this is a good first equation. Next up, we've got J2. So we're going to do the same process, J2. We do sum of torques. Actually, let me give me a little bit more space here. Oops. It's going to look really similar. So I'll go through it pretty quickly. J2, sum of torques equals J2 theta 2 double dot. I go back to the free body diagram. I have a positive Tn, then I have a negative TB2 and a negative TK. So we put those definitions in. And same thing as before, we can move all the theta 2's to the other side. It is negative here and negative here. So that means it's going to be positive when I bring it over and add it. And that is our second equation. We have, like we thought we would have, we got two second order equations. In total, it's a fourth order system. We have two outputs. We've got theta 1 and theta 2, and they have some relationship between each other. Been good. Been good. Okay. Now this is not correct. Oh, you wanted to point it out? Correct. It's really easy to make mistakes. So make sure you got the negative, negative. That becomes positive. Yes, thank you. I was afraid no one would point it out, so thank you. These are my two equations. Now, are these single input, single output? Which means one input, one output. I look at it, both of them have two inputs. Therefore, I can't just create a transfer function for the first one. I can't just make one transfer function for the second one because I have these two inputs. Now, we can still, combine these. I can have J1 S squared plus B S plus K times theta 1 equals K theta 2 minus Tn. This is when we're in the S domain. I can do the same thing for the other one. So I can put it in the S domain, but I can't create a transfer function because I've got two inputs. Now, what we can do, and I'm not going to go too far into this yet, there's a lot of algebra that we can do. We can, let's say I don't care about theta 2. I just care about theta 1. There is a way for us, once we're in the S domain, to actually solve for one and plug it into the other one. And you can cancel out some things. And like if there's one variable we really care about, we can simplify it and actually create one large transfer function that gets rid of one. That's where we were going. We just won't cover it today because it's a little bit too much. But if I have it in the S domain like this, it makes the algebra possible. So I can take it and form it into whatever I want it to be. In this case, though, right here in this moment, I don't have a transfer function, but I could if the question asks something of me. Sound good? Okay, so I will post these slides. I know we did learn a lot. We did some translation. We did some mechanical, rotational as well. I'm going to hand out a couple of problems. So I feel like you'll be a group and you'll be a group. I'm just going to hand out 2 problems. It's a group problem. You don't have to solve it by next class. In a week from today, on Thursday, you're going to work, you're actually going to present your problem. So I'm going to give you some problems for you to solve, just one problem as a group. You can work on it right now if you want to. You can work on it at the end of class next time. I don't really care, but we'll have some presentations then. And what I'm hoping for is that one of your members doesn't just present the breathe part. Okay, now that is important, but you're gonna all take turns kind of writing out the different parts of the body when you present it. So let me, you know what, I'll hand them out. I'm just gonna post the rest of the slides. I'm not gonna go through them. We don't cover it too much, but like what happens if I have 2 springs in parallel or dampers? It talks about it a little bit, so you can check that, but we don't use it too much. So this is basically the end of my lecture. I will pass out the problems and you can work on it or take off if you want to. Sound good? Okay, here are the problems. Okay. Oh no. Then I have other problems. Obviously, I've taught this with many full classes before, so I have other problems. But for my we need to go on the Discord. He's in there. Close to that. I feel like I got to breathe. What today? It's Discord. It's in the local room. I can double check that. The what? Yeah.